Masses are the same, but this is 25 centimeters. That's okay. At 25 meter, 25 meter, 20 become 25 meter. Now what is the work done? Work done is same as the change in potential energy. So we have to find the initial potential energy of this configuration and potential energy final of this configuration. Imagine a unit mass here, here the force 4m, here 2m, and the effective is 2m along this direction. And here also, over here there is 2m due to 2m, and here there is due to again m and 3m. Due to m here, m is here, and the resultant is due to 2m here. And therefore this force here is equal to G due to 1m, m by r squared. And whereas this force is due to 3m is equal to G 3m by r squared. Welcome my dear friends. Today in this video we are going to discuss the questions from two chapters, Gravitation and the System of Particle Rotation. Now question number 1 from Gravitation, that is there on the board. Three masses 200 kilogram, 300 kilogram, 400 are placed at the vertex of an equilateral triangle. The side is 20 meter. They are rearranged on the vertex of a bigger triangle, 25 meter, and with the same center. The work done in this process. Now, earlier, the arrangement we can do like this. It's an equilateral triangle of side at 20 meter. And mass, three masses, 200 kilogram, 300 kilogram, and 400 kilogram. Separation are the same. Question is, we are going to rearrange so that bigger triangle of 25 centimeter. Now this is transformed into this one like this. Masses are the same, but this is 25 centimeters. That's okay. At 25 meter, 25 meter, 20 become 25 meter. Now what is the work done? Work done is same as the change in potential energy. So we have to find the initial potential energy of this configuration and potential energy final of this configuration and subtract. We get the work done. So the work done. Now we have to calculate for the initial potential energy. G m basic formula is equal to potential energy is equal to minus G m1 m2 by r. The potential energy formula. So it's equal to minus r is same for all of them and therefore minus G by r into adding three terms m1 m2 400 into 200 plus 200 into 300 plus 300 into 400. So G m by r, there are three terms, and out is r is 20. So here you can see that this is 20. This is the initial potential energy of the system. Gravitational constant is given. R is given. Therefore, this is equal to minus gravitational constant 6.7 into 10 raised to minus 11. R is equal to 20 into this term into 10 raised to 4 plus 6 into 10 raised to 4 plus 12 into 10 raised to 4. Final potential energy. Final potential energy, if you do it the same way, you final. This time is the same, this time is the same. Only difference is instead of 20, it is 25. That's okay. For this situation, minus 6.7 into 10 raised to minus 11 by 25 This time is 8 into 10 raised to 4 plus 6 into 10 raised to 4 plus 12 into 10 raised to 4. Now numerical calculation is there definitely, and you can say this is the next part is the work done. Work done we already told that this is equal to Vf minus Ui, that is the work done. The change in delta U, that is the work done, and work done you can compute from this. Compute from this, substitute this numerical value, and this value on calculation, you can see that on next page if you want. Otherwise you calculate and the numerical calculation. Yield the result 1.74 into 10 raised to minus 7. So the option is correct. We can go to our next question. Next page, the calculations are there if you want, but no need of it. But given below are two statements. A satellite is moving around Earth in very close orbit of Earth's surface. The time period of revolution satellite depend upon the density of Earth. Now we have to want to see whether it depend on density of Earth or not. For which we are given the time period like this. T is equal to pi into root of R of Earth. The closer orbit R is the radius of the Earth itself. G is equal to, we can replace it by Gm by small g. Capital G, capital M by R squared. Where capital G into, this is equal to 4 by 3 pi R cube into density by R square. So this will cancel out, this is the formula, 4 by 3 pi G R rho, that is G value. Now instead of this G in our equation, substitute this value, it's equal to 4 by 3 pi G R rho. And here we can say R will cancel out, and definitely T depend on rho. And what does the statement say? Statement remove around Earth and orbit close to the Earth's surface. The time period of revolution depend upon the density of Earth. That is true. This statement is true. Statement 1 is true. And what about the statement 2? The time period of revolution satellite given close to Earth's surface, where R is the radius of Earth and G is the accelerator due to gravity. And 2 pi into Re by G, that is true. For a close orbit, that statement is true. And therefore this one is also true. Both statements are correct. So the option is 4. Both statement 1 and 4 are correct. Okay. Next one. Escape velocity from a spherical planet A is 10 km. Escape velocity from another planet B, whose density and radius 10% more. We have to write down the escape velocity in terms of density and radius. Density and radius must be there in the expression. You know escape velocity, root of 2 G M by R. Now replace M and bring in density and radius. Equal to root of 2 G 4 by 3 pi R cube density by R. Therefore, V escape, these are constants. R cancel out, you can say that proportional to root of R squared rho. Escape velocity depends on R squared rho. Then, in our first case, R is R, rho is rho. In the planet B, radius and density 10%, radius 10% of that of A. Escape velocity from another planet B, whose density and radius are 10% of those of planet A. 10% mean is equal to R2. We can say this is RA. We escape A proportional to root of RA squared rho A. Escape velocity for second planet B proportional to RB squared by rho B. Now VA is given to you, first planet. VA is given to you. Now dividing, this is question number 1 and this is question number 2. 2 by 1 gives 2 by 1 gives you VB by VA and VA is 10 given to you. It's equal to root of RB by RA whole squared, RA whole squared into rho B by rho A. And how much RB? Only 10 percentage. 10 percentage means RB by RA as per the statement. RB by RA is equal to 1 by 10, 0.1. And therefore this is equal to 1 by 10 whole squared into by 10 is equal to this on calculation. This on calculation root of 1 by 10 cube. That is equal to 10 by, VB by 10 is equal to this much. Therefore, VB is equal to 10 the root of 1 by 10 raised to 3. This is kilometer and convert that into meter per second because the answer is in meter per second. So it's equal to 10,000 kilometer into root of 1 by 10 raised to 3. And this on calculation, the value is found to be this one. Go to our next question. Net gravitational force at the center of a square is found to be F1. When 4 particles having masses m, 2m, 3m, 4m are placed at the 4 corners of a square as shown in figure, and it is F2 when position of 3m and 4m are interchanged, then F1 by F2. F1 is the force on the particle at the center. Net gravitational force at the center of a square, at the center here. In this situation, the distribution of masses are like this. The distribution is like this. The force is F1. Now we have to get that force. Here you can see that if you imagine a unit mass here, the force 4m, here 2m, and the effective is 2m along this direction. And here also, over here there is 2m due to 2m. And here there is due to, again, m and 3m. Due to m here, 3m is here, and the resultant is due to 2m here. And what is the angle between them? It's a square, and therefore at this point, the angle between them is 90 degrees. And what about the force? The force is given by Gm by r square. Basic formula. Here 2m and 2m, and therefore here G into 2m by r square. Here our r is the half of the diagonal of this. Suppose this distance is r. This is r. I am telling. This is r. Here this is r. This is r. Then the force here, net force here F1. F1 is, these two forces are identical because of 2m. And therefore what is the force due to 2mg, 2m by r square. Here also g 2m by r square. Angle is 90 degree, and therefore the resultant is equal to root 2. Therefore root 2 into g into 2m by r square. This is our F1. in this situation. In second stage, what they did, they simply interchange two particles. When position of 3m and 4m are interchanged, these two are changed. So we are going to draw the second situation. Here is 3m and here is 4m. They are interchanged. Whereas here is m and here is 2m. Now here you can say that due to 2m, net force cancels, and additionally here that is due to 1m. Whereas here is 4m and this is m, and the net force is due to along this direction is due to 3m. Sorry, 3m. Here is 4m and here is m, and the net is due to 3m. And therefore, this force here is equal to G due to 1m, m by r squared. And whereas this force is due to 3m is equal to G, 3m by r squared. And the angle between them again 90. And therefore, we have to find the resultant of that too. The resultant here is F2 is equal to root of Gm by r squared whole squared plus, because they are mutually perpendicular, plus root of 9 Gm by 9, Gm by r squared. G into 3m, strictly speaking is better. I have to write like this. G into 3m by r squared. This on calculation, root 9 plus 110. Root 10 Gm by r squared. That is our F2. Now you know F1 and F2 both are there, and we have to find F1 by F2. F1 by F2 is equal to F1 by F2 is equal to root 2 by root 10 is equal to 1 by root 5. Now the question is, what is the numerator? Compare alpha is equal to 1. Compare alpha is equal to 1. So the option is 1. Initially, a satellite of 100 kilogram is in a circular orbit of radius 1.5 RE. The satellite can be moved to another circular orbit of radius 3 RE by supplying alpha into 10⁶ joule of energy. The value of alpha is. Now, earlier, our satellite is in an orbit, radius is 1.5 RE. And we are raising that to another orbit or radius 3 RE, double. Now, what is the work done? Work done is the change in energy of the satellite in these two situations. And what is the expression for energy of a satellite is a bound state, satellite revolution. And they were definitely negative. And the formula, you know, the energy of an orbit, a satellite in an orbit is given by minus G m by 2r. That is the formula you must remember. And therefore, in first case, energy in the first case, E1 is equal to minus G m by radius of the orbit is given as 1.5. 2 into 1.5 r. Energy in second case, second orbit is given by minus G m by 2 into 3 r. The radius as a whole is given to you. Now the question is, what is the work done? Final minus initial. That I'm doing G m by r2 re 1 by 1.5 minus 1 by 3. And this on calculation. This on calculation. The work done on calculation is given by substituting. We are given all the values there. And here R is given R is given, and energy supplied is given to you. Energy supplied is given to you, and acceleration due to gravity is given to you. Now you know acceleration due to gravity G is given by Gm by R square. Therefore, capital G, capital M is equal to capital G, capital M is given by G R square. Is equal to capital G, capital M is given by this term. Now, that can be replaced, and here you can see what is the value of G capital M is given by small g R squared by 2R 1.1.5 minus 1.3 into M. Now substitute the values. And here alpha into 10 raised to 6. The other part substitute, all the values are there, and everything is given to you. Substitute and get the answer for alpha. And alpha on calculation is found to be 1000. The calculation you can see on the next page. Now it is given there like this. And we are given all the terms and get the answer for that. If you want, you can get the calculation from the next page. Okay. So change in the total energy is the work done. That's what we did.